Hello everybody. Today is Wednesday the 26th and we are going to take a look at lesson 11-5 and that introduces the idea of geometric probability and area of sectors. And a sector is actually just a little portion of a circle, okay? So those are kind of the two main pieces to this lesson. Let's start out with geometric probability. Now, I think most of you, all of you, know that probability in general, very generally speaking, in order to figure out the probability of something happening, you take the chances of that happening, or the amount that you want, divided by the total. Okay? So in geometric probability, typically it has to do with figuring out the probability of a shaded region. So we do P and then just put shaded in parentheses. The way that you figure this out is basically the same way that you would figure out any probability. You take the area of the shaded region, or the region that you want, divided by the total area of the entire figure. Okay? And that's how you figure out the probability of landing in that shaded region or what have you. Okay? So the first example goes along with this, and I think you guys will pick this up relatively quickly. Let me get some shapes here. So if I have this figure, and then I have this figure, so we're talking a circle within a square. There we go. And if I say that this measurement right here is 12 inches, we want to figure out the probability of landing in the shaded region. Okay? So let's say this was like, I don't know, maybe a game board or something, and maybe you were throwing a dart at it, or maybe this was a spinner and you wanted to spin and land in the shaded region. Okay? So what we're going to do is, we first need to figure out what the shaded region would be, the area. So that would be the square minus the circle. That's what's going to give us the shaded region. So if we look at the area of the square, that's base times height, we know that that's going to be 12 times 12, or 144. Okay? Then, if we want to figure out the area of the circle, well, if this is 12, then half of that would be 6. So that would make the radius 6 inches. So we're going to take pi times 6 squared, or 36 pi. And when you round that to the nearest tenth, you get about 113.1. Okay? So if we take 144, minus 113.1, the area of the shaded region is about 30.9 square inches. Okay? That's what we kind of did in 11-3 too. All right, so now we want to figure out the probability of landing in there. Okay, so the probability of the shaded region, we are going to take the shaded portion divided by the total, which in this case is the whole square. That would be like our game board, so to speak. Okay, so we just figured out the shaded region. That was about 30.9. And we are going to divide that by the region of the square, which in this case is 144. So when we divide those, 30.9 divided by 144 is about 0.21. And I believe that your book leaves it like that, so it's about a 21% chance. But I believe your book leaves it as a decimal rather than putting it into a percent. Okay, so that's how you figure out geometric probability. So, I mean, you already know most of it, but now it's just kind of taking it that step further and dividing it by the total. Okay, the next part of this, area of a sector. Okay, well, basically, a sector is like a pie piece. Okay, so this little part right here, that's the sector. Why they don't call it something else, I don't know. All right, so what you need to figure out the area of the sector is the radius of your circle, which you guys know. And then we're going to use this central angle. We talked about the idea of a central angle when we first looked at polygons and areas of polygons. So I'm going to give that n degrees. All right, so the area of a sector is this. N divided by 360 times pi r squared. Okay, so that would be the area of the circle. All right. Okay, so let me show you an example of where you might use this. I'm going to use my shapes again here so I can get a good circle. So let's say we have this circle. And for this example, we first of all want to find the area of the shaded region. Then we want to find the probability of that shaded region. So this one is going to almost be like a spinner on like a game board, like you spin the arrow in the middle. So if that's our center, let me see if I can get this right here. I have one angle, that's a 90. This one is 45. This one is 80. Then I divide this, I don't want that to look like a diameter though, because it's not. Maybe go like that. Okay. This one is, I know it doesn't look it, but it's 60. 30, I should flip those. 35, 60, and 50. That's a 60. Okay, and the shaded part is this one and this one. Okay. Okay, so let's figure out the area of the shaded region. So this one, it has two sectors in it. So we're going to use our formula, only we're going to take the total degrees of those sectors. So we have a 45 and we have a 35. Okay, so when you add those together, you get a total of 80 degrees. Divided by 360. Oops, I forgot to put the radius on there. Whoops-a-daisy. 18. That'll be the diameter, of course. Times pi times 9 squared, because 9 would be the radius, correct? So now if I go 80 divided by 360, I'm going to hit equals. Then I'm going to go times pi times 9 squared, or 81. Looks like the area of the shaded region rounded to the nearest tenth is about 56.5 square units. Okay, so I just use that sector formula. Now I want to figure out the probability of landing in one of those two sectors. Okay, so I'm going to take that area that I just found, then divide it by the area of the circle. Okay, so the area of the circle itself would be pi times 9 squared. We haven't figured that one out yet. So pi times 9 squared is going to be about 254.5. Okay, now we can use that to figure out the probability. So 56.5, that's the shaded, over 254.5, that's the total. So if we take 56.5 divide by 254.5, we end up with about 0.22 or 22%. Okay? The final piece of this has to do with another new shape, and that is the area of a segment. Why they use that word segment, I couldn't tell you. I wish they would have used a different word. But a segment, if this pie piece is a sector, the segment is this little sliver right there. Okay? So it's a little portion of that sector. So really, to figure out the area of a segment, so I'll write it like this, what we're going to do is figure out the area of the sector minus the area of the triangle. Okay, so the triangle is this part right here that I'm coloring it in yellow right now. That's the triangle I'm telling you, or I'm talking about. Okay, so let me show you one quick example of this, and that should do it for today. All right, so I have my circle, and in this circle, I'm actually going to draw a hexagon within the circle. Like that. And then I'm going to color in 3 of these. Okay. And then this is going to be 12. All right. So what we want to do is kind of actually the same directions as the previous one. First of all, we want to find the area of the shaded region, then find the probability of landing in that shaded region. Okay, and that should do it. All right, so if I were to draw in a triangle, and this is going to look very much like those examples that we did in 11-3 with the apothem and all that kind of stuff. So in a hexagon, one of the central angles, you're going to take 360 divided by 6. So one of these central angles is 60 degrees. All right, looks like a radius is going to be 6 because this diameter here is 12. All right, so we can figure out the area of that whole sector with just that information. So the sector is 60 divided by 360 times pi times 6 squared. So if we plug that in, 60 divided by 360 equals times pi times 6 squared. For the sector, we get about 18.8. Okay? Now we need to figure out the area of this triangle. Well, we need base and height, don't we? So if this is a 2n in this 30, 60, 90 that I've created, this would be n, so this would be 3. This would be 3 times the square root of 3. So really, this whole base here is 6, right? All right, so the triangle, 1/2 times base times height. I'm going to run out of time here. I'm going to get cut off. I'll continue this. Hang on.